So first of all, thank you for the organizers for the opportunity to speak here. And this is a talk about golden mean matroids. The title just sounded cool, so I went with it. And of course, this is joint work with my advisor, Stefan von Zwam. So first of all, what is the golden mean? Well, that is the positive solution to this equation over the reals, which comes out to 1 plus square root of 5 over 2. And a matroid is said to be golden mean if it can be represented by a matrix over the reals, where every non-zero subdeterminant is a power of the golden mean up to a sign. And there is a really nice characterization of the class of golden mean matroids, due originally to Dirk Vertingen, with a proof later on by Rudi Pendavingh and Stefan von Zwam, that the following three conditions are equivalent for a matroid. First of all, M is golden mean. Equivalent to that is that M is representable over GF4 and GF5. And then finally, M is representable over GF5 over all your square fields, so GFP squared for all primes P. And for GFP for all primes P, such that P is congruent to plus or minus 1 modulo 5. So this is one of several results that are very analogous to Tutte's characterization of the regular matroids, because we can see, well, what kind of matrix is this representable over? And the regular matroids are representable over the reals by a matrix that is totally unimodular, meaning every non-zero subdeterminant is plus or minus 1. And then we also can see, well, what kind of fields is the matroid representable over? Regular matroids are representable over all fields. This result and many of these other analogous results use the idea of partial fields, which I'm not really talking about in this talk, but it's sort of lurking in the background behind everything that I am talking about. So one of the things that we can ask about this class of golden mean matroids is, what is the extremal function, which was just talked about. So if M is a minor closed class of matroids, the extremal function HMR is the maximum number of elements in a simple matroid of rank at most R. And there is a conjecture about the extremal function for the class of golden mean matroids from Stephen Archer in 2005 from his PhD thesis. His conjecture is that if the rank is not 3, then the extremal function for your class of golden mean matroids is R plus 3 choose 2 minus 5. And then the conjecture is that there's one exception to that, one sporadic case when the rank is 3, the extremal function is equal to 11. And the conjecture goes on that for R equals 3, maximum size matroid is the Betsy-Ross matroid. And that for rank not equal to 3, the maximum size matroids belong to one of 3 families of matroids. Let me show you what those families look like here. So these are the names that came in Archer's thesis. And I actually got these names from Michael Welsh's thesis, who did some work on golden mean matroids as well. So this D sub n here just represents the signed incidence matrix of a complete graph. So it's the n by n choose 2 matrix whose columns consist of all the n tuples with 2 non-zero entries. One is 1, one is positive 1, one is negative 1. So we see here that we have something very graphic with some other stuff on top of it. And so we want to be able to see if there's a way that we can verify this conjecture and see if there's a tool that would help us with that. And that tool has been graciously provided by Jim Geelan, Bert Gerards, and Jeff Whittle with their matroid structure theory. In particular, what Stefan and I have started calling the Template Theorem. So in a 10-minute talk, I definitely do not have time to go into all the details, or hardly any details, really. So I'll just give you a very brief sketch idea of what this is about here. So if we look at a minor closed class of matrix representable over a finite field, then those highly connected matroids are what's called low-rank perturbations of frame matroids or their duals. We heard about frame matroids yesterday. A low-rank perturbation just means, well, I take this frame matroid and I look at a matrix that represents the frame matroid, and I add a matrix to that matrix, and the matrix I add to it has low rank, and so the resulting matroid is a low-rank perturbation of the original matroid. So I said F actually has to be finite, so this is all part of Gerards and Whittle's profound structure theory of matroids representable over a finite field. So what is a template? Very, very basic idea is that it's essentially a recipe for building matroids. And just a few minutes ago, I was thinking maybe a better analogy is a buffet, because what you do is you are allowed to take different things, add some rows. So you take your matrix that represents a frame matroid, you can add some rows to it, add some columns to it, but you can choose, when you add the columns, add the rows, there are different vectors you can add to it that come from the subgroups, and different things like this. So basically you take this matrix and you add some bells and whistles to it, add some things to it, but each template allows you to build different matroids, infinitely many different matroids. And the template theorem says that the highly connected matroids in a minor closed class are built using a finite number of templates. Okay, so a finite number of templates. So using that, Stefan and I were able to prove this result, which is really just a corollary of a result by Jim Geelan and Peter Nelson, that if you have a quadratically dense minor closed class of matroids, and that class is representable over a finite field, then there's a set of templates, set T, and these templates are often denoted with capital Greek letters here, such that for sufficiently high rank, the extremal function is equal to the size of the largest simple matroid of rank R that conforms to some template in that set. Okay, so if we can figure out, well, what are these templates for the class of golden mean matroids, we can say, well, which one builds the biggest matroids, and we're done. So what we did for that, though, is we said, well, this class of golden mean matroids is contained in a larger class. And before I describe that class, let me give a quick definition here. The characteristic set of a matroid is the set of numbers k such that the matroid is representable over some field of characteristic k. So with this definition of characteristic set, and with this bit of notation, if we let P represent the set of prime numbers, and with the characterization of golden mean matroids that I gave on my first slide, we know that that every single golden mean matroid has characteristic set P union 0. So we decided to look at the class of GF4 representable matroids that have this characteristic set P union 0. And a really nice thing about the template theorem is that if we have if a matroid that is not representable, that is not in this class, that is not representable over fields of all characteristics, if it conforms to some template, the template theorem says that that particular template is irrelevant for the class of golden mean matroids. So we were able to say, well, what templates allow me to build a matroid that does not have this characteristic set? We found some excluded minors for that. And if a template allows me to build one of those, then, well, that's out. And so let's look at the templates that we have left and which ones give us the biggest matroids. So based on that, we have this result here. So for matroids of sufficiently high rank, so we have to add this small preface to these results. the maximum size matroids representable over GF4 with characteristic set P union 0 are exactly those three families that Archer conjectured for the golden mean matroids. Okay, so we know that these three families are indeed golden mean matroids, and we know that the class of golden mean matroids is contained in the this class here of GF4 representable matroids with characteristic set P union 0. That means that this proves Archer's conjecture for matroids of sufficiently high rank. So the maximum size golden mean matroids are those three families, verifying Archer's conjecture for matroids of sufficiently high rank. So that's nice. And so basically proves this conjecture, since a lot of these results we want to know about the eventual growth rate, the eventual extremal function for things of sufficiently high rank. And I've actually been telling some slight lies in this talk. I said, well, we wanted to do this, therefore we did this, and we wanted to do this, therefore we did this. Actually, what we wanted to do is we wanted to look at the class of matroids representable over all fields of size at least 4, and this sort of rolled out of it. So the class of matroids representable over all fields of size at least 4, we only get two of the families. So one of the families, you're required to have something that has the golden mean in the field. The other two are representable over all fields of size 4. And some additional work in preparation. I think I'm close to out of time here, but we want to be able to characterize all the highly connected matroids in this class, not just the extremal ones. That's done for the primal case. The Betsy-Ross matroid conforms to some of the relevant templates. And then all that glitters is not golden mean. The Pappas matroid is not golden mean. It conforms to one of these templates. It's representable over GF4, not GF5, but all fields of size at least 7. And we're still working on the dual case, so. And that's all, so thank you.
Are there any questions for Kevin? I definitely have one. Okay. So you actually get equality. You characterize the matroids for which equality holds?
Yes.
So,
yeah.
So
each of the families corresponds to a template. And
isn't there an issue with the connectivity reduction? I thought that the theorem, as Jim and I stated it, doesn't work to get equality. You know that if you beat a certain extremal function, then you beat it in the highly connected case. But what if you attain it?
Actually, I haven't thought about the details about your results in a while. So I'm just going off of the result in one of our papers, which was this corollary of your result. I think I'd have to look at the details of that and think about it so much. But
are there any more questions? Oh, at the back.
So you were saying that these three largest classes that you found were, and that included that theorem there, which all had to attain the upper bound R plus 3 choose 2 minus 5. Were there other quadratic maximal golden mean matroids or GF4 representable matroids that were not quite that big?
There should be, yes, because we are looking for some. We are still trying to characterize all of the highly connected matroids here, and the way these templates work is there's one set of columns that if you make that set of columns as big as possible, then the matroids you get from it is going to be as big as possible. But if we want to characterize all of the highly connected ones, then we actually make that set of columns as small as possible, and we can make something else bigger. So there should be things that roll out of that that will definitely not be these extremal matroids, but they quite possibly will be minors of them, I believe. Not sure if I exactly answered your question, but.
What would be maximal?
Yeah, okay.